look here in the front cover of our book, the mass of a proton is 1.67 times 10 to the minus 27 kilograms. So our mass is 1.67 times 10 to the minus 27 kilograms. And our charge is 1.60 times 10 to the minus 19 coulombs. Okay? And our change, this sucker is going to be velocity initially here of 0, velocity final here, I don't know. That's what I'm looking for. Our change in potential energy is going to be minus 9 volts because it's going to move from here to here. Okay? So, think about that for a second. Now, we think about the equations that we're going to need here. What we need is change in kinetic energy is equal to minus QT delta V. So our change in kinetic energy is going to be the negative of 1.60 times 10 to the minus 19 coulombs times the minus 9 volts. Okay? So 1.60 EXP 19 negative times 9. The two negative signs divide out. I get 1.44 times 10 to the minus 18 joules. And change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. Now, velocity initially was 0. So what I get is 1/2 times the mass, 1.67 times 10 to the minus 27 kilograms, v final squared, is equal to 1.44 times 10 to the minus 18 joules. So I divide by 1.67 EXP 27 negative, multiply by 2, take the square root. I get the final speed to be 4.15 times 10 to the 4 meters per second. Now, if we did the same thing with an electron, okay, an electron is going to start here at the negative plate. And it's going to want to move in this direction. So for the electron, okay, we want the change in electrical potential to be plus 9 volts. Its velocity initially is going to be 0. We want velocity final. Okay, so the change in kinetic energy is going to be the negative of a minus 1.60 times 10 to the minus 19 coulombs times 9 volts. So the change in kinetic energy is going to be a plus 1.44 times 10 to the minus 18 joules. Notice it's the same change in kinetic energy. And I'm going to go 1/2 times the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms, times V final squared is equal to 1.44 times 10 to the minus 18 joules. So 1.44 EXP 18 negative times 2 divided by 9.11 exp 31 negative, take the square root. I get V final for the electron to be 1.78 times 10 to the 6th meters per second. Okay, kind of make sure that you can see that. Yeah. Now, the electron ends up moving much faster than the proton, but that's because the electron weighs a heck of a lot less than the proton did. And they're both going to start from different positions. They're going to move in opposite directions. The proton, we'd start from rest and move it toward the negative plate. The electron, we'd start next to the negative plate from rest and it would move toward the positive plate. Okay, so kind of absorb that in, guys. Pull that down here into the pictures. I scrolled up to get some equations. Okay, guys. Let's think about attaching a battery to a parallel plate capacitor. A battery is a device that uses chemical energy to generate charge separation. And it's labeled with electrical potential differences it can create. Okay? So if I have a parallel plate capacitor here and I attach it to a 1.5 volt battery, the side that's attached to the positive end of the battery, that side of the parallel plate capacitor becomes positively charged. The other side becomes negatively charged. And the potential difference across the parallel plate capacitor is going to equal the potential that can be generated by the chemical reaction inside the battery. Okay? And now we have created a uniform electric field between the plates of a parallel plate capacitor. So, the size of the battery and the separations of the plates dictate the strength of the electric field. So, if the electrical potential, okay, V plus minus V minus plus 1.5 volts, E times D. For a parallel plate capacitor, the electrical potential always equals the strength of the electric field times the distance between them. Now, the battery controls the electrical potential, okay? If I were to now have that battery attached and I were to pull the plates further apart, since delta V is set, if I increase D, the separation, the strength of the electric field is going to decrease. If I were to decrease the separation, the strength of the electric field would increase. So last time we were looking at a set charge on the plates, okay? A set strength of electric field, and if the field was set and we changed the separation, the voltage would change. Here the voltage is set. If we change the separation, the electric field changes. So if you maintain the electrical field and you increase the distance between the plates, the strength of the electric field goes down. Now, let's look at these figures. Okay, here we have the positive plate at plus 100 volts, the negative plate at 0 volts. Equal potential surfaces in between them. Okay, here we've made the positive plate our 0 potential and the negative plate minus 100 volts. If I move from here to here, I have a potential difference of 50 volts. Okay? Same thing here. What these three diagrams do for us is they remind us that where we set our electrical potential to be 0 is pretty arbitrary. But if I have the same potential difference between two plates, okay, it doesn't matter where I call the positive, where I call 0 electrical potential, the electric field lines always point in the direction of decreasing electrical potential, and if I were moved from here to here, I would have a decrease of 50 volts. Here to here, decrease of 50 volts. Here to here, decrease of 50 volts. Okay? And a positive test charge would move in this direction. A negative test charge would want to move in the other if it's released from rest. Okay? It doesn't matter. The electric field inside all of these capacitors is the same, no matter how I label what's my 0 potential point and what I label as a positive potential point or a negative potential point. Okay, let's look at Stop and Think problem 25.4 on page 702. All right, now A, B, C, D, and E. The question asked in this problem is where is the potential the highest and where is the potential the lowest? Kind of rank them. Well, A and B are the same distance from the positive plate, so they're going to be at the same potential. D and E are at the same distance from the positive plate, they're going to be at the same potential. The highest electrical potential is always closest to the positive plate, so these two have the highest potential. This one is the next highest, and these two have the lowest potential. Okay? So, let's start by looking at problem 9, the conceptual problem, and then we're going to do 2 more problems, and then we're going to move on and kind of finish out the chapter. Conceptual problem 9 here. It says it shows 2 points inside a capacitor. Let V equal 0 be at the negative plate. What is the ratio of V2 to V1 of the electrical potential? Well, if the whole plate is, well, it's 0 here, and we know that at 1 millimeter, 2 millimeters, 3 millimeters, we have equal potential surfaces. Here at point 2, the electrical potential should be 3 times what it was at point 1. So the ratio of V2 to V1 should be 3, because we have equal potential surfaces, and this one's 3 times further away from the negative plate than point 1. It says, what is the ratio of E2 to E1, the electric field strength? Well, this is a parallel plate capacitor. The electric field strength in here is everywhere the same. So the ratio of the electric field at point 1 and point 2 is going to be 1, because the electric field strength is everywhere inside there the same. Okay? Now, let's think about the other 2 problems I want us to look at. I want us to look at problem 24 and 26 on page 710. All right, if we look at problem 24, it says 2 2 centimeter by 2 centimeter plates form a parallel plate capacitor, and they're charged at plus 708 nanocoulombs and minus 708 nanocoulombs. It says, what is the electric field strength inside and the potential difference across the capacitor if the spacing between the plates is 1 millimeter and 2 millimeters? Okay, I'm going to erase the board. You guys look at that problem. Think about it for a second. Okay. So, let's draw ourselves a pretty picture. Okay, so our positive plate is plus 0.708 nanocoulombs, and the charge over here is a minus 0.708 nanocoulombs. We know the strength of the electric field is equal to eta over epsilon 0. Okay? So eta is equal to the charge, Q, divided by the area. So the charge here is 7.08 times 10 to the minus 10 coulombs. And the area is 2 centimeters by 2 centimeters, so that's 2.00 times 10 to the minus 2 meters squared. So 7.08 exp 10 negative divided by 2 exp 2 negative squared. I get eta to be 1.77 times 10 to the minus 6 coulombs per meter squared. E, the strength of the electric field, then is going to be 1.77 times 10 to the minus 6 coulombs per meter squared divided by 8.85 times 10 to the minus 12, and that's coulombs squared over newtons times meters squared. So divided by 8.85 exp 12 negative, I get 2.00 times 10 to the 5 newtons per coulomb. That's the strength of the electric field. Okay, so one of the things that we were asked is, what is the strength of the electric field? The second thing we were asked is to find delta V for a 1 millimeter separation and delta V if we had a 2 millimeter separation. Well, delta V equals E times D, so it's 2.00 times 10 to the 5 newtons per coulomb. And 1 millimeter is 1 times 10 to the minus 3 meters. So I would get 2.00 times 10 to the 2 volts. If I had a 1 millimeter separation. If we had a 2 millimeter separation, it would be 2 times 10 to the 5 newtons per coulomb times 2 times 10 to the minus 3 meters. So I get 4.00 times 10 to the 2 volts. Okay, so not too bad, right? We can do that. Now the other problem I wanted us to look at was problem 26. Same page. So let's look at problem 26. It says, a proton is fired with a speed of 200 200,000 meters per second from the midpoint of the capacitor toward the positive plate. Show that this is insufficient speed to reach the positive plate, and what is the proton speed as it collides with the negative plate. Okay, now let me draw us a pretty picture, okay, because we're going to need a pretty picture. So here's the picture that we're dealing with. Okay, we have a proton right here with a V initial. V initial is given us as 200,000 meters per second, and that's its magnitude. It's going toward the positive plate. Okay? If we look at the picture, this is a 500 volt electrical potential, and this is a 0 volt electrical potential, and we're at the midpoint. Now it doesn't tell us what the separation is, so I can make the separation anything I want. So I'll make this, let's make this 1 centimeter, and this is at 0 centimeters, so this is at 0.5 centimeters. Okay? Now, what it asks us is, it says, show that this is an insufficient speed to reach the positive plate. So if I think about the position where V final equals 0, okay? It's telling me that that's going to be before it hits the positive plate. So I know that the change in kinetic energy has to equal the negative of Q delta V, okay? And so our kinetic energy final is going to be 0. Our kinetic energy initially is 1/2 times the mass of the proton, which I keep forgetting is 1.67 times 10 to the minus 27 kilograms times 200,000 meters per second squared, has to equal the negative of Q, which is 1.60 times 10 to the minus 19 coulombs, times delta V. So 1.67 EXP 27 negative times 200,000 squared divided by 2. So I get a minus 3.27 times 10 to the minus 17 joules has to equal the negative of 1.60 times 10 to the minus 19 coulombs delta V. Notice the negative and negative divide out. Divided by, so 3.24 times 10 to the minus 17 joules divided by 1.60 EXP 19 negative. gives me a delta V of 4.9 times 10 to the minus 3 volts. Well, the difference between the midpoint and here, this would be 250 volts, and that's 500 volts. 4.9 times 10 to the minus 3 volts is a heck of a lot less than 500 volts. That poor proton doesn't go anywhere at all before it turns around and starts going in the opposite direction. Okay? Now it asks us, what would be its speed when it collides with the negative plate? So, V final if S final is 0, the negative plate. Okay? So, change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared, has to equal the negative of 1.60 times 10 to the minus 19 coulombs, and the change in potential is minus 250 volts, because it's going from 250 volts to 0. So I have 1/2 times 1.67 times 10 to the minus 27 kilograms times V final squared minus 200,000 meters per second squared. If I wrote that out in scientific notation, it'd probably be easier for us to keep track of. So it's 2 times 10 to the 5. Okay? That has to equal, notice that the negative and negative cancel out here and here. So 1.60 EXP 19 negative times 250. I get 4.00 times 10 to the minus 17 joules. So I multiply by 2, divided by 1.67 EXP 27 negative. So I have V final squared minus 2 times 10 to the 5 meters per second squared is equal to 4.79 times 10 to the 10 joules. I'm going to add to it 2 EXP 5 squared. So solving for V final, I get 2.96 times 10 to the 5 meters per second. It's sped up. Which is what we would expect. And V final there, remember, is just a magnitude. Because when we do energy, it gives us magnitude. Okay? This is how we do particle acceleration. What they do, okay, if I wanted to accelerate a positive charge, they actually make a hole in this plate. And they shoot the positive proton through. It enters the electric field, it experiences that force, and it gets accelerated. And if you put a little hole here, then it can come out the other side moving faster. So, particle accelerator, introduction. Okay, guys. Let's scoot on up here. Let's talk about electrical potential around a point charge. We know that as we move out from a point charge, the strength of the electrical field decreases. Okay? We're not dealing with a uniform electric field if we're looking around a point charge. That means that the equal potential surfaces around a point charge are not going to be equally spaced. In fact, as you move out further, they're going to be further apart. So you notice here to here to here, okay? It drops off as a factor of R. So it's KQ over R, or Q over 4 pi epsilon 0 R. The dotted lines represent equal potential surfaces, and it drops off as a factor of R. So if we look at, grab this back down. We look at this diagram, and we look at this question. The stop and think question says, rank in order from largest to smallest the potential difference AB, AC, and BC. A and B are on an equal potential surface. Since they're on an equal potential surface, the difference AB is going to be 0. So the difference in electrical potential from point A to point B is 0. B and C, we're going to have an electrical potential, okay, difference. In between A and C, we're going to have an electrical potential difference, but they're going to be equal to each other because, okay, A and B are on the same equal potential surface. So the difference in electrical potential A to B is 0. Between A and C, and A and B and C are going to be equal to each other, okay, and something other than 0. All right, now let's scoot it on up. So AB equals AC, which equals 0. AB is equal to 0. AC equals BC, which is greater than 0. So let's look at problem 43 at the end of the chapter. Okay? Now, I'm going to be a little lazy here. Let's look at problem 43. Problem 43 says, a proton's speed as it passes point A is 50,000 meters per second. It follows the trajectory shown. What is the proton's speed at point B? Okay? So, let's work on the board. Okay, now, our speed at point A, okay, is 50,000, so 5.00 times 10 to the 4 meters per second. Now, it moves from a point A to a point B. Our change in electrical potential is minus 10 minus 30 volts, so a minus 40 volts. Our change in kinetic energy, which is equal to 1/2 m V final squared minus V initial squared, okay, is equal to minus Q Q delta V. Now, we're told that this is a proton. So I have 1/2 times 1.67 times 10 to the minus 27 kilograms, V final squared, minus 5.00 times 10 to the 4 meters per second squared, has to equal the negative of 1.60 times 10 to the minus 19 coulombs times minus 40 volts. Okay, so 40 times 1.60 exp 19 negative equals, notice the negative sign and negative sign cancel each other out, multiply by 2, divide by 1.67 exp 27 negative. I get V final squared minus 5 times 10 to the 4 meters per second quantity squared is equal to 7.76 times 10 to the 9, and that's going to be meters squared over meters squared over second squared, because I have a coulomb times a volt. Okay? So I'm going to add to that 5 exp4 squared. So V final squared is 1.02 times 10 to the 10 meters squared over second squared. Take the square root, and I get V final to be 1.01 times 10 to the 5 meters per second. So I went from 5 times 10 to the 4 meters per second to 1.01 times 10 to the 5 meters per second. It went up, which is what we would expect, because it moved from a region of higher electrical potential to a region of lower electrical potential. Okay? It went in the direction of electric field lines. Okay, guys, that is the end of the chapter. There are some problems at the end of the chapter that I would highly suggest that you look at. 1, 3, 12, 16, 24, 25, 26, 27, 29, 43, and 54. Okay? And I will, of course, be giving you a problem sheet to do with this in class next time we meet. And we have a test which will go through this chapter the following week. Okay? Bye-bye.